my chat filter still on. Ewen. There we go. Ewen, I'm gray. Hey everybody. I don't know if you can hear the vacuum. Probably. It's over. It's over now. It's loud at the end. Okay. What is up? Oh, my linear is up. Oh, there's vacuum again. We got that 2013 YouTube gamer channel chic with the mom vacuuming in the background. Good day. Let me do some fluids. I have a new problem set. Oops. Keep that up. I think it's not too bad. Okay, I think it's not too bad. There's one that I hope we can get to, that I'm very excited about. But I think it should be fun. So I gotta grab my problems, which are somewhere. I don't remember where they are. Oh, actually I should check when these are... Oh wait, I brought it up here. When does this due? It doesn't say when it's due. Great. Sorry. There's a GIF that he put. I love that he put a GIF, but not the due date of the homework. Wait, let's see. Course count. Sorry, this is riveting, I'm sure. 19. Okay, so I have 5 days to work on this. That's fine. That's fine. I have a midterm exam on the 19th. Okay. That's fine. That's fine. I don't know what he's gonna put on this midterm, because we've done... we've done, like, 2 things. Anyway. Sorry, I gotta pull this up. We're doing hydrostatic stuff. Which means pressures, basically. Pretty much only pressures, funnily enough. Okay, do we want to do... Let's see, what is the gauge pressure in pounds per square inch of that? What is the pressure in ATM units? Or we could do manometers. I feel like... let's do the first one. We're gonna be doing a lot of manometer problems. I love saying manometer. There's in the data analysis class I took, we had to work with micromanometers. Such a great word, micromanometer. Like a Muppet. It's like a Muppet thing. Micromanometer. Okay, so pressures. Neglecting the compressibility of water, what is the gauge pressure in pounds per square inch at a depth of 15,000 feet below the surface of the ocean? Alright, well... A. We want to say pressure equals rho g h. Which is kind of nice, because it's not that hard. I have to find the density of water, which I should probably know, because I'm taking a fluid mechanics class. But, you know... Use my handy dandy. Oops, I can't get it out of my bag. Out here. My 44-page reference document. Why have to... Proud of him. I don't think he's gonna enjoy that I printed it not double-sided. I didn't really have a choice. There's some pages in here that I definitely don't need. Okay, pressure, I don't need that. We're gonna have to scroll a little bit. Oh my god, did I just say scroll? Jesus Christ. Sorry, I'm like an iPad kid. Where are these? Okay, that's what a triangle is. I don't know why that's in here. I don't know why... Okay. Guys, do we really need to put vector addition in this? This is why this is 44 pages. Oh my god. No. Series, that's fine. Whatever. Integrals. Oh my god, this is just 3 pages of integrals. What is happening? Why are there so many integrals? Okay, that's statistics. That's just a blank piece of paper. Centroids. It's all just like garbage. Okay, the centroids are not garbage. I was never book smart. To be fair, I'm not particularly book smart. I'm like intuition smart. I just think about the relationships between things. So I'm like, I know what gravity is. I'm money smart. Okay, where? Okay, I found fluid properties. Where's water? I just need the density of water. In slugs per feet cubed? What are we doing? Pounds per square inch. I'm so tired. Oh. Specific weight, pounds per square foot. I think that's right. It become 2:30 p.m. Oh well, it's 12:30 here. It's not that. Okay, density H2O equals 62.4. Now, pounds force or pounds mass? I think it might be pounds force. I had to guess. Pounds force per feet cubed. I will have to say E equals 62.4 pounds force per feet cubed times gravity, which is 32.2 feet per second squared. So that gets rid of that. We're getting close to that. Times the height. Wait, why is... That's not gonna work out. Hello? Wait, density? Oh, pounds force has a... Wait, but pounds per square inch is pounds force per inch squared. Maybe specific is not. Specific gravity units. Alright, English units. I'm a hater. What? Sorry, specific weight. Bro, different things. Newtons per meters cubed. Not useful. Oh, it's density times standard gravity. Oh, wait, so I don't need gravity. Lol. That's why. I guess this is gamma. Let's use gamma. Is that literally just 1.94 times? Okay, whatever. 32.2. That's fine. Okay, so we got pounds force and then times the height, which is 15,000 feet. That goes away, and we'll get and then times 12 inches over 1 foot. There we go, squared. Just a unit conversion thing, but you know, it's just the basis of density, so it's a good thing to check. Oh. Alright, the basis of pressure. Hopefully we'll see a G or A at the end of PSI implies that the value is a gauge pressure or an absolute pressure. Okay, gauge pressure then. Sometimes you will not see this, only the units, but you'll be told it. Okay. 15,000. That is very lots. Sorry. Very lots is not a... That's like an insane amount. 10 to the 12th? No. I overestimated. 10 to the 9th? What? 92? I did not mean 92. Not 10 to the 92, sorry, I'm tripping. 10 to the 8th, okay. So 1.3... I guess it would make more sense to have it in 10 to the 6th. So let's do that. 134.78. Oh, he's gonna be a sig fig maniac, isn't he? I'm guessing. Maybe he isn't. How many are we given? I guess we're given 2 there. And that one's to 3, so it should probably be to 2. Probably not that many. We'll just say 135. Times 10 to the 6th. Giving you an extra one for good luck. And then ATM units. So what's an ATM? What's an ATM guy? I'll look it up. It's in my book somewhere, but I don't know where it is off the top of my head. ATM unit. That's in pascals? What? I want in... Does it have a conversion? PSI? Or do I have to turn PSI into pascals? Because that would kind of suck. Let me see. Viscosity, temperature... specific heat unit. Oh, these are different. Wait, 1 PA. Second. No, that's viscosity. Area, power, pressure. Oh, here we go. Actually, easier to find it here. You should stream for 8 hours. I can't do that. I have things to do. Unfortunately. Well, not really unfortunately. I would be like kind of dead. I mean, I have streamed for almost that long twice. On both my debuts I streamed that long. But I don't make a habit of that. I would only stream like once a month if I streamed for 8 hours. I tend to stream longer in the summer though. Because I don't have to like do things. Debut again. Well, I just debuted, so I'd have to make a new model. I mean, I do want to make a new outfit. Okay, 14.6696. 69, nice, okay. Debut every day, bro. I can't even stream every day. I'm on that grind set. I literally just forgot what this was. 135 times 10 to the 6th PSI times, what did I say? 14.696 PSI. The 1 ATM. Lots of ATM. 24/7 debut. Oh my god, subathon length? I don't think anybody would sub to me, so I don't think I could do a subathon. 14.696. There's one thing I wanna try. Or one thing I wanna start developing. That's a lot of atmospheres. Does that make sense? How much is 1 atmosphere? That's like the general... How deep is 15,000 feet? A mile at 15,000 divided by 5280. Okay, almost 3 miles underwater. Does that like make sense? This is like 9 million times the pressure we feel at the surface. I don't know if that makes sense. That feels like... Well, I have no way of knowing if it makes sense or not. You know how long that was? I don't know. Years? Ooh, okay. Cool. That one's all chill. Hopefully I can do unit conversions right. Actually, let me see if I got the right answer. I forgot that he gives some answers. Oh god. Oh god, this is my one of my officer chats is blowing up right now, and I do not have the brain power to do fluid mechanics and think about that. Please don't ever think that getting that. Okay, no. I got it wrong. Wait, what the is yeah, 660 PSI. That is way too many. Okay. What was I doing? What was I doing, bro? Maybe my density of water is clearly incorrect. Multiple weeks. Okay, this set the sub time all the way down to 1 second per sub for it to end. I don't get money like that. I'm not in it for the money though. What is up with my density of water here? Pounds per square inch. Okay, let's say if I did it in slugs. Do I want to get a slug? Sure. One slug is one. Slugs are in foot-pounds. But that's not gonna help me. The 12 squared is the thing that's bad. So what's up with that? Because I'm still gonna have... we get that 12 squared down. It's in pounds per square inch is the thing. Oh, he's the guy with the AI. Oh yeah, Neurosama. I know that guy. Or I know the VTuber. Huh. Why? How is that so... This isn't bad. Well, pressure is just rho GH is the thing. What is up with that? 8 per second. Let's see. If I multiply, it's 1.94 slugs times 32.2 is 62.468, which is that. Am I just goofing it at a depth of... Hello? Someone tell Vito there's a problem with my AI? What AI are you writing? AI is funny. What the hell is up with this? What the heck? It's not pounds, it's not gonna be pounds mass. Like way too high. You would be so crushed. Humanity would not be having a good time if going down that deep, going down 3 miles was that much. Let me check. Ooh, no. This is literally just multiplying 3 numbers. Okay, I'm gonna come back to that one. We'll see if I ruin all the units on the next one too, then then it's not a fluke. This is loading. It's the error message that Neuro says if something... Oh. Something breaks in their code. That's funny. Let's see. I'll do... 1, 2. I don't really want to do the absolute pressure on the top of Mount Everest. not as interesting as tire blow up. Not that this one is also terribly interesting, but it's fine. Okay, so the tire of an airplane is inflated at sea level to 60, okay. So we know that the pressure equals 60 psi at gauge pressure, which means we can figure out how much stuff is in there. Anyway, what was all of that? You being like, damn, I wish I could have got your stream while I was still streaming. Well, the way you were talking about it made me think you ended. You'd said, hey, I'm still streaming. I would have gone, oh, that makes sense. And then I would have gone. I had an event from 8:30 to 3 p.m. So I was a little busy, and then I had to do work stuff. What is the pressure within the tire at elevation? Okay, so if we do this, delta P equals rho, because rho is not changing. Gravity is, well, assuming the tire does not expand, I guess I could just say, do I want to account for gravitational change? Assumption. How much does gravity change? How far up do you have to go to change the grav field? Gravity less than an altitude of 1 inch. Okay. No, not escape gravity. I just want to... At what elevation does gravity change? Changes at any... Okay, that's not useful. It doesn't change non-negligibly. Only... Which are located 2,000 kilometers, only has a slight change in gravitational acceleration. I'm just gonna say that the gravitational change is negligible. And all I said was doing the thing again above. I don't know. Sorry, I don't know what to say. Grav delta is negligible. Negligible. Rho G delta H. Maybe it's the feet that are the issue? But like, let's see, 60, I guess I don't even really need to, yeah, no, 60 minus x, that's, sorry, x minus 60 equals rho. Do I know about air? We have a general air. Air's density is gonna change by the temperature to whatever you say, negligible. What do we think about air? How do we feel about air density? I think we feel like it changes with temperature, which means we need a... I think I'm thinking about it too much. Oh, air standard. Oh, here we go. Temp density in slugs per feet. Let's do that one. When am I gonna stream... What is that? Balatro? I've never heard of that game. Wait, I'm gonna look it up. Balatro. It's a poker-inspired roguelike deck builder? Wait, that sounds cool. I don't know anything about poker. But that looks cool. I kind of want to play Inscription on stream. I feel like that would be really fun. I'd love it. It's not that much about poker. Oh, okay. I like the art. looks cool. Like the funny little clown guy. I'll have to try it. I want to play, the other thing is the hands you play, but it tells you how to make the hands. Oh, okay. That's cool. We're chilling then. If it tells me, if I have to remember, it's like Mahjong. Like I really want to play Mahjong, but I have to remember like a bunch of stuff to play Mahjong, and I'm like, I don't have the brain space to remember a bunch of different hands. I'm sorry, guys. Okay, air. Are we just gonna assume that the temperature doesn't change? That's really kind of stupid. One stream, full run of Inscription. Oh, I would die. It's such a damie game. I wanna stream a bunch of different games over the summer. Sorry, I don't know if I should be doing this temperature difference or not. And if I did do the temperature difference, how would I do that? Let me think. We would use it's inflated at sea level. Let's do this. Let's say there's a density delta. Because for a gas, it's very much not negligible. Or for air, I guess I should say. So we're gonna say at up there, so density is 1 point that in kg. Wait, that's kg meters squared. I don't want that. Oh wait, shit, it only gives me, okay, I read it wrong. Getting over it? Oh no. I could not play that. I'm not a gamer game. That's a gamer game. Properties of air at atmospheric pressure. Oh, here we go. Getting these all out of order, which is not great. Elden Ring? Also probably not a game I could play and have fun with, but I like watching Elden Ring. Subnautica? Oh, I do want to finish. Did I play that on stream? I can't remember if I played that on stream or not. I could have sworn I played Subnautica on stream, but maybe I didn't. Maybe I just started a run by myself. Okay, it gets colder. What's our standard? Our standard is like 25 degrees Celsius. It's like the standard. Oh, altitude. Wait, here we go. Okay, at 30,000, it's negative 24.6. Wait, but I want it in pounds. Can I get it in Fahrenheit, please? Can I get the altitude table in Fahrenheit, guys? Please. Guys, please. Not they hate me. Where's my altitude table in Fahrenheit? This is so sad. Look, they give me like all this stuff in... It's like beautiful. 15? What if I just did it in that and then I converted to... You don't want F? You want K? No, no, no. We want F. Wait, do I? Wait, maybe you're right. We're in... But we're talking about pressures, so when they give me temperature in C, they're giving me Newton meters pressure. And I need pressure in pounds per square inch. Wait, temperature, SI, English 59? Not, that's sea level conditions. That's, okay, that's a start. Okay, but we know it starts at 60. And the density at 60 is... So this is like P high minus 0.002377 slug per feet cubed. Oh, I could just use a specific weight. Let's do that instead. 0.0. Oh, shoot. Gravity's gonna be the same for both of them. We'll just call it gamma h. Minus 0.07651. Pounds force per feet cubed. And then times 30,000. Lethal Company? You're suggesting games that are not damie games. I know Umbra's got me on the damie games. I do want to play that Shapes game that someone suggested. That one looks cool. Despite flow analysis, I want air. Guys, can anyone please give me air density? This is stupid. Maybe I missed it. Maybe it's in the page before. 44 pages and they don't even give me the answer I need. The info I need. I shouldn't say answer. Critical point properties. No. Air density is 0. Do I need to use like a table? If I need to use a table to convert this blows. I'm thinking too much about this. There has to be an easier way to do this. Well, this is how I do it. If I can just see, this is one of the things that I find annoying about this course. Is it's like, okay, I understand how to do this. I understand what I need. I don't know where I'm supposed to find it. And the issue is like, it's not even like, oh, I can't find it. Let me go look for it in all of the places that it exists. It's like, no, you need to find it in a specific place, but we're not going to tell you where that specific place is. So here you go. Waste like half an hour trying to find this value in a way that's acceptable to us, but we're just not going to tell you where it is. It's such a waste of time. Sorry, I'm a hater right now. We can go away. Let me do a problem that's actually not just unit conversion. This one, are they given? Determine an equation, thank God. Or, okay, do we want to do a Venturi flow meter? Or, no, that one's easy actually. I lied. We're gonna do the harder one. The Venturi flow meter is like, oh, as the area gets smaller, the pressure drops. Some fluid dynamics problem that he's having us do before we're learning dynamics, but I digress. This guy's a little bit quirky. Yeah, they want you to fail, kind of. It's okay though, because I'm not gonna fail. I know what I'm doing. Roughly. Okay, flow rate can be determined by means of flow nozzle. Oh yeah, this is the same kind of thing. It's just pressure differences, but I wanted to do a manometer instead of a they gave the 2 tubes example, so then there was just a height difference here. That's a little less fun. I mean, this is the exact same kind of thing, but okay, determine for an equation for PA minus PB in terms of the specific weight of the flowing fluid, the specific weight of the gauge fluid, and the various heights. Okay, so this is the gauge fluid. Oh, it says it here. Yeah. All right, so we need to figure out, so the pressure here is going to be determined by it's going to be determined by this, right? The depth of this. Well, I guess you could also say that it would be determined by this depth? Gnome! You gnomed me. Hi, Egg. How's it going? Hope you're doing well. I guess it's also this depth, huh? No, that would be like the pressure down here. I don't really care about the pressure down there. Oh, but I can use the pressure this distance to figure out the pressure here, which is the same as the pressure here. Okay, so P2 equals P3. I guess I could probably just set up a bunch of equations like that. And P1 equals P2. Sup? Thanks, my guy. Well, P5 is going to equal P4. This is like one of those games where they're like, oh, this man is married to this person, but this person isn't married to this person. Who's married to who? Okay, so what is P? Wait, can we solve for any of these things? I guess I could probably solve for P3. Equals, it's gonna be the density of, but like, don't we care about like this little bit? Maybe not. Do we not care about that bit? I thought we did pressures from, I guess you could probably do pressure from the bottom up too. No, you can't, because gravity doesn't act that way. So why is it giving us... I always found these problems very, very interesting. I'm gonna have to ping pong around to different points. I really don't like that they're not giving us a height here. But I mean, obviously we don't need it, but I want it. Just because I want to be able to say like, oh, this equals this. What if we did get a height here? What would we could say... Let's say that this is a height. Maybe we can, like... Car alarm's going off. Maybe we can, like, subtract some stuff out. Okay, so this pressure... Okay, I'm gonna use it as a dummy variable. So P1 is gonna equal the specific gravity of 1 times H minus H1. Right, so that's how much liquid is pushing down here. And that's going to equal P2, which equals... which equals P3, which equals the specific gravity of fluid 2 times H minus H1 minus H2. Yeah, we're getting somewhere. We have some relationships between things. And that's going to equal the pressure at P4, which equals the pressure at P5. Did I just say they're all equal to each other? So like the pressure here, because it's like a force thing, like this force is going to equal this force, you know? And like this one is going to equal this one because we're in the same altitude in the same fluid. Maybe. Well, not maybe. That one I know is true, but this one also would make sense, right? Like the pressure here would equal the pressure there. But I said, wait, the pressure at P3 is not equal to the pressure at P4. Okay, that's the difference. That's the difference. Don't do that. But the pressure at P4 does equal the pressure at P5, which equals gamma 1 times H minus H1 minus H2. Ooh, so we can like substitute some things, I guess? So what do we get? I I have some extra H's in here that are a little funky. Yeah, because let me think about this. So this... The H's should cancel out. I think they might. Do I need like the pressure here? Not really, huh? Yeah, because then I'd have to define another height below that. We really just need this. That kind of shape going on there for our heights. Well, okay, so we've got H minus H1, which we like. And I don't like this one. That one's fine. Oops, I didn't put a subscript there. Okay. What if I factor things out? That could maybe work. Or what if I... but then I have to solve for... If I want to like plug this in, I'm gonna have to put in pressures here, and those are not my friends. We don't know those. Okay, well, we want PA minus PB. That's the other thing. So the pressure here. Why did I not start with that? PA equals this times the height. Oh, it doesn't equal that, actually. Because, okay. Yeah, because it's... B is gonna be... Wait a second. B is gonna be... Wait, they should be equal to each other, shouldn't they? Because we're not measuring at the Venturi. Or, yeah, like, we're not measuring, like, at that little flow meter. We're measuring, like, before and after, so it should be the same. Should it not? Maybe it shouldn't. That's very interesting. I guess how can we write PA? What do we know about PA? The pressure here. What is going to cause the pressure here? The pressure here is going to be caused by... I guess it's less about this fluid and more about this fluid moving through it, right? That's where we're getting a pressure? The nozzle, which is an obstruction, creates a pressure drop. Okay, well... We just have to relate all these heights to each other. Let me see. How can we get this related to this, though? I guess we know that the pressure here is going to be more than the pressure here. So like P3 equals P4 plus rho GH. Now what rho and G? Well, it'd be rho 2 times H2. I think. It still doesn't give us the pressure at A and the pressure at B. Oh, maybe that's what... Wait, am I silly? The pressure at A is going to equal... equals like P1 plus... plus H1. And the pressure at B is going to equal, maybe that's how we do it, P5 plus rho 1 H2? No, H1 plus H2. So if we subtract these, we can start to get somewhere. Equals P1 minus P5 minus rho 1 H2. So now we have to figure out what P1 and P5 are. So let's get rid of this. And we'll start from this and see if that can get us anywhere. I like that better because it's like, okay, we know that and we know that. Those are what we're actually trying to solve for. So then P1 is equal to, I guess we'll just use the height. That dummy variable we have. So it would be row 1 times h minus h1. But we have an h in there, and we'd rather have that h2. So we can write this, we can also say that equals p2. And p2 equals p3, which equals, okay, we're getting there, which equals p4 plus gamma 2, or is that gamma? Maybe, yeah, no, maybe. I've been saying gamma. Gamma 2 plus h2. Okay, slowly. Now P3 equals that, P4 equals that. P4 equals P5 equals, we're gonna minus, and the h's are gonna cancel out, I think. Row 2 times h minus h1 minus h2? That's what we had before, I think. Okay, so then we say PA minus PB equals, no, it's gonna be, oh, we were so close. No. Because there's a, wait, no, this is 1. It does cancel out. Let's go, baby. Let's go. Okay, wait, yes. Okay. Oh, yes. Uh-oh, wait, but like, wait a second. Wait a second. Oh no, we're chilling. No, we're not. Wait a second. How do I want to write P1? So I can write P1 like this. But I need this form of P1 in here. So but I need to put P4 in there. Wait, but it's gonna get rid of P4. So if I say this, sorry, P4 plus, yeah. Oh yeah. Wait, what? Wait, I think I goofed somewhere. So P1 equals this, so P4 plus Y2 H2 minus P5 equals P4. I don't think it's that. Okay, I might have done something wrong. Let's see, I probably set two things equal to each other that shouldn't be equal to each other. So if it's in the same fluid, I can set it equal to each other. So 1 can equal 2, 2 can equal 3, and then 3 has to equal addition, and then 4 can equal 5. One can equal 2, which can equal 3, which means I don't really need to even describe it like this. But maybe it can't equal, maybe in here this thing, at this interface, it's something goofy. Let's see, maybe I can't set, are pressures equal at a fluid interface? I mean, if not, it's gonna violate, what? Wait, what? Wait, what? It just said it's not equal. Okay, that's a colloid. Egg. Okay, it has to equal. The pressures have to be equal. The forces are equal. Pressure's a force. But it's not just the difference in height here. There's no way. There has to be something else. Oh wait. Wait. Minus. Wait. No. We're chilling. Oh my gosh. Wait. No. Wait. We're chilling. Oh my god. Sorry. I'm so excited. Wait. H2? What the? I trust it. Sure. H2. Wait. I need H1 in there. There has to be an H1. Did I forget an H1? But we got the density of this fluid. Let's go, baby. Let's go. Okay, wait. So PA equals P1 plus an extra height, sure. PB equals P5 plus both of the heights. Yes. So like the difference between A and B is well, P5, you know, is a different pressure, but like we have the difference between 1 and 5, and then yeah, an additional. Okay, that makes sense. That should be H2. Oh man, why do I only have H2? I need an H1 in there, otherwise they wouldn't have given me an H1. Okay. So P1 equals gamma 1 H minus H1, okay. That equals here, which equals here, we're chilling. And P3 equals this, plus, sure. P4, 5, yeah. Okay, maybe let me like write it out a little bit bigger. I'm like kind of doing myself a disservice here. So P4 plus, I'm gonna write the same thing. Hold on, I'm gonna write the same thing. Or am I subtracting the right thing though? That H1 is just really... There's gotta be an H1 in there somewhere. Maybe I'm not locating 2 properly? Because I'm saying P1 equals P2 equals P3, which should be the case though. Because we're not changing depth. Okay, let's think about this. Pressure equals, right, this dude H. So as we go from, but it's at an interface, so I don't think it would change. In that case, it'd be the same here. And then this point would be, oh. Wait. It would be the same there, and then but then we would only have H1. Is that true? We can define, so... Would it be the same there? it's right there. Okay, let me try to do another one. Let me mess around with the old brain cells for a little bit. Okay, this is great. This is another. I don't know why these fluid, these ones where it's like, here's a bunch of liquids in a manometer, just makes my brain go, huh? Liquid? In liquid? No. To be fair, I also haven't looked at any examples of doing these, so I'm kind of just balling out. But that's how we do it here. Okay. Liquid A weighs... okay, so that's its specific... That's its specific weight. Oh, you can't read it. Here's a picture. Don't look at anything. There we go. Liquid A weighs that much, and it weighs the other much. The manometer is shown is mercury. If the pressure at B is 30 psi, find the pressure at A. Okay. Okay. I'm gonna do it symbolically, because I don't really want to deal with... This is gonna be H1. This is gonna be H2. This is gonna be H3. Okay, so we start... We say pressure. Now we start... This is kind of important. By kind of important, I mean we wouldn't be able to do the problem if this was not true. So, you know, good to just throw that in there. What else? I guess fluids are static. So the thing that I don't like is he's having us write some assumptions where like the problem statement will state an assumption. So like, for example, we had a problem that was like, it was like, once this reaches a steady state, blah, blah, blah. And he was like, assumption, fluid has reached a steady state. And I'm like, okay, you can say that, but the problem statement says that. Like, we don't need to assume that if they told us that that's what it is. Because, like, it's kind of like stating your givens when the problem statement gives, and he doesn't want us to state our givens. So, like, to me, that's a given. That's not an assumption. But, anyway. Okay. Actually, do they need to be incompressible for this to be true? Yes, because we have to say their densities don't vary. But, yeah, I mean, that's saying it weighs one number means that its density doesn't vary, but whatever, okay. That's fine. All right, so let's say what is the pressure at B? The pressure at B is going to equal... What is it going to equal? Well, it's going to equal the pressure here, which is... I guess I should probably give these points names. This is 8.5. 8.25. 8.5. What's F? Sure. So it's the pressure at 8.5 plus this B times H1 plus H2. Easy enough. Okay, so then what's the pressure at 8.5? That's going to equal the pressure at 8.25 plus of mercury times H3. Right? Because we go down a little bit and we add that much. Then what's the pressure at A? Pressure at A... Oh, sorry, pressure 8.25 is going to equal No, we need to say A. Because 8.25 is kind of like our highest point, so we're going to base pressure at A off of that. Whoops, 8.25 plus... how much are we adding? H3, so sorry, this... H3 plus H2. Okay. So we can solve for 8.25 to get 8.5 in there. So we're gonna say this. Or we'll do this. So pressure... I guess I should probably solve for pressure B equals P A.25 plus M H3 plus specific at H1 plus H2. And then PB equals... Okay, so if I solve for 8.25, it's going to be PA minus this. Oh, this is easy. What is happening? Why is the other one not... Why did the other one not work like this? There we go. Solved. Oh wait, not exactly solved. What was find the... Okay. This was like not too bad. Okay, maybe these guys aren't so bad. I can do it. I believe in myself. There we go. Okay, I don't have to do anything more for that. Okay, that's cool. Should we go back to that? No, I can't do that. Not right now. Okay, should we do... Ooh. Ooh, okay, so we have one... I'll put these up on screen. Maybe no one's gonna care, but I'm gonna care. They're a little cut off. Wait, let me... They both look a little interesting, actually. Which, you know, kind of rare. Rare and based. Okay, so we just gotta choose one of these. So we can have height of an airplane with... So this is a linear decrease in temperature question. And this is like... so they're both about like incompressible substances for the air, which is good because I wanted to do a problem about that. But one of these is an adiabatic environment, and maybe that one's more exciting because we're still calculating a pressure here. This one is a height. I think B might be a little harder because I have to also plot something. That's cool. I like that. Let's do that. Let's do the second one. But I also, there's a distributed load question next, and I really want to do that. Okay. So at ground level, the atmospheric temperature, the atmospheric pressure is 83.2 kilopascals and 25 C. Okay, we're in C. Thank God. Calculate the pressure on Pike's Peak. Who's Peak? Pike? Peak, Pike, Pike's Peak. Wait, let me get some chocolate. At an elevation of 2690 above the city, assuming an Okay. Okay, so if it's incompressible, we're gonna have the density of air as a function of temperature. Now, I could make an equation for that. I don't know if that's what he wants, though. What do you think? Look up? Not look up? Make some shit up? You cannot assume that the air is incompressible. Sure. You can assume the air is static and solve for the appropriate form of PZ. Sure. You're just told how the atmosphere behaves in an adiabatic atmosphere. You need to translate this into an equation. You might find it useful to refer to a thermodynamics textbook. Wait, a thermodynamics textbook, bruh. Okay. You need an equation for the state of the air in the atmosphere. Well, like, do I go find one? Or do I have to make it up? Let me go out and measure some air real quick. Or I guess that's a little bit facetious. I wonder if there's one in my supplemental information handout. There might be. We'll check there first. I don't know if they give me the equation. They might give me a graph. And I certainly don't want to back out an equation from a random graph that somebody gives me. Okay. I've eaten my chocolate. Let's see. Okay, A is going to be a little easier, because we know what incompressible is. An adiabatic is a type of compression. I know that from thermo. And it means that it's a very quick compression that conserves work, I think. It conserves something. I was gonna say temperature, and I was like, it does not. It's like, it looks like this or something on those graphs. Like the pressure versus temperature graphs. It looks like something like that, I think. It's like quick. I don't know. I remember you can light things on fire with it, which means its temperature's higher. Anyway. So pressure. I guess I should do pressure as a function of Z equals, sure, rho GZ. Okay, solved. No, I'm kidding. Plus, let's see, plus 83.2 kilopascals. Okay, we can put gravity in there. That's a good start. 9.8 meters per second squared. It's density. Times meters, I guess. Yeah, Z. Okay. That's something. Now the only hard part of this problem is this. Plot the ratio of pressure to ground level pressure. The ratio of pressure to ground level pressure. So we're normalizing it to, it's gonna be like +1, I guess. Intercept of 1. Okay. Let me look. Let's look in the book. The chonky packet. Actually, you know what? We can go on a field trip. Let me pull it up. Supplemental information handout. Thermo edition? Properties of liquids and solids. Why is it giving me the water content of apples? What? I need the freezing point of milk? Why? Why do I need the water content and latent heat of fusion of Swiss cheese? When am I ever gonna need to do that, guys? Please don't tell me my thermo class is using lettuce as a building material. Maybe for what's it called? Bomb calorimetry. That's the only thing I can think. Okay. I think if I crop this well enough, we can go on the field trip. My whiteboard turned into a blackboard. Let me crop it like right. No, it doesn't matter if I crop it. It's fine. This is the pages of integrals. I'm scrolling. So this is not air yet. Fluid properties water, fluid properties gases. Here we go. So we have air here. We have this sideways graph of, what is this? I don't know what that is. Here? Yeah, so we have this. I mean, I could do a regression on these values, I guess. Wait, what if I just did that? That might be the closest thing to like a good thing that we have. An adiabatic atmosphere. PV, whoa, P, whoa. P over density does not vary with height. If a lump of air is moved to a higher level, its pressure and density will change so that the density, that the pressure over, what? In which F? What's that? What's F, bro? Oh, P. Its pressure and density will change so that P over density to the Y. It is possible to calculate the rate at which temperature decreases with height. So I have to find, okay, we can use the, that means that this, well, what is the Y? What is this? Is that specific? Is it specific weights? Smiles? I don't know. Maybe it's that. Man, I don't know what that is. I kind of wish. Okay, field trip is over. Let me see if I can find what that is. I don't really want to do a differential equation for this, please. I just want to know what that weird little thing is. For real air. Oh, okay, wait. It says 1.4 gamma. I think it might be gamma. Kind of your properties of plane areas. I'm gonna have to put them goddamn sticky notes in this thing. Fluid properties, gases. Here we go. For real air, for eel, it doesn't give me. It doesn't give me the density. I don't know. I'm gonna assume it's the specific weight, which we can calculate for the bottom, and then we can just say, oh, this thing is this thing, and then it just stays the same. For this one, I'm gonna say regression PZ. So sorry, density of with T. Regression of points. Oops, sorry, engineering lettering. Should we do some MATLAB? I could do that. I'd be down. be a good brain exercise. Points from sup handout. Now, I don't know if it's gonna be like linear or like what's up with that, but we'll do that. There's a MATLAB. This is good though. Let me see how many things there are also in this. 6. Oh, okay, no, good. I don't have to do that. 6, 7. Whoops, 7 looks cool. 8. Yeah, 10. Oh, 10 looks hard. 11 is the super hard one. Oh, 11 is a super hard one, but I really want to do 11. I think 11 is a buoyancy problem, but I'm not sure. New script. Oh, I moved my thing around. Okay, that's fine. Here we go. Let's do some MATLAB, shall we? Do I have anything that's gonna... No. Oh, I like that it doesn't show up on that capture. You wanna show up there? No? Can I refresh? Here we go. Okay, so we need to start with... Let me actually open up one of my older labs that I have. I need to be a little careful. Oops, not that one. Where would that be in? Here? 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 Yeah. I think this one should be okay. Yeah. Okay, I'm gonna steal this. This is homework 2. We're gonna save this. I'll have to move them. There we go. This is flu. Homework 2. Okay. Sorry, underscore. Perfect. Okay. Okay, this is gonna be temperatures. Oh wait, yes, change that to temps. Change this to densities. I love that I can do that. And then we're gonna put in all these numbers. Oh, okay, it's in C. But they gave it to us in C, so we're chilling. I think it started at 25, right? So I don't have to do past that. I can probably... Yeah, I can do this. So we want to go from 25 to... 5 to 100. And we want to put it on the densities. Okay, so 25 is... riveting. Oh man, there's not a German 985, are you kidding me? Where's my favorite streamer? My favorite retired streamer. There we go. Hopefully those match up in size. That is not a 9. There we go. So I don't care about that. I don't care about the inverse fit. And I don't care about that. I want to actually just display... Yeah. I don't know if this is going to show up. Whatever. Add to path, I don't care. Oops. Okay, is that... It's kind of linear. It's not really super linear. It's kind of hard to tell. tell if this would be linear or not. It looks pretty linear. But it could be... What if I tried second order? Oh, second order looks a lot better. We're gonna say it's second order. I don't want to plot that. What is it? Can I display it? Oh, I can. Okay. Whoa. Oh, I put my axes weird. We'll have to fix that. I want from 25 to, I guess, 100. And then from like, I don't know, 0.9 to 1.2. Yeah, that's clean. Okay. I don't know though, because like, so it's a second order fit, and, or I put a second order fit on it. And so like the thing about it is like you can, it's hard to tell if it would be second order or not is the only thing. I don't know if it is second order, but we're gonna go with it because it looks better. Here, wait, I'll show. I don't know if I can... Here, I'll take screenshots of it. So, I took second order, and let's do the first order one. It's just one of those things where, like, in my data analysis class, we talked about when you're going up in orders, you know, there's sometimes a temptation to just do the orders until it, you know, has a very low, like R value or whatever. But that can kind of be bad. Okay, so this is what, oops. Shoot, there we go. I think that's my normal. Sort of, yeah. So yeah. Let me... Wait, no, not that. Bring it back. I meant to do it on this. There we go. So yeah, so like... This one is like not... I mean, it's okay. But like this one fits like better. But I don't know if that's just because it's like that, you know? I don't know. Well, I'm gonna go with second order. I'm gonna say, second order seems better. So then P of Z, or density of T equals... Oh, what? Wait. Oh, I see. Equals x squared, or sorry, t squared minus 0.0048 t plus 1.3026. There we go. Oh, you know. Just me and my row of t. And so then, you know, that's what that is. I don't really know what else to say. And then if we plot, we can plot the what's it called? They're asking for like the normalized one. The adiabatic one, I don't really want to do that right now. I'm gonna put a star on that. That one's not finished. Was 4 finished? 4 was sort of finished. I'm gonna put like a star C for calc 3A. We go back to 3A. Wait, I want to go back to 3A. Wait, I want to go back to 3A. Wait, let me try to do this without the height. I think I might be able to define this without the height if I just define it in terms of like P5 and stuff. Let's try that. Let's try that. This one is chillin'. This is like using the sort of definition that we were doing on the problem 4, not definition. I mean the methodology, I guess I should say. So P1 equals, what are we doing? Equals P2. Don't even try to describe it as anything other than that. Equals P3 equals P4 plus row 2 H2. So that way we have no H's. And then P4 equals P5 yeah. Oh. Wait, that's literally it. PA minus PB equals P4 plus... Yeah. Sorry, P4. I'm gonna substitute one thing in at a time. Minus P5 minus row 1 H2. Wait, but it's still H2. Where's H1 in this? Wait, did I say PA? Yeah, there's no H1. Well, I mean, I guess that makes sense. But why would they give us an H1? Let me think. It would sort of make sense that, like, that, but it doesn't only the difference between them matter? Isn't that the whole point of a manometer? Only the difference between the two liquids kind of matters. I don't know, every time I do this I feel like I'm just getting H1 and H2. Yeah, no H1? Lol. That's fine, I'll leave that. So I guess the other way we did it was, you know, not incorrect, but... Let's see. Okay. Yes, 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 yes. Okay, this one looks way cooler. This one looks way cooler than the other one. I don't want to do a weird concrete wall problem, okay? I want to do other concrete wall problem. It's like the cow with the little... this thing. It's like you have two choices. A, B, concrete wall. Concrete. That's me. I'm the cow in that example. That's truly what we all are when we study fluid mechanics. Okay. A homogeneous, 4 foot wide, 8 foot long, rectangular gate weighing lots of stuff. We gotta make a free body diagram. We are chillin'. This isn't hard. I'm just gonna call it theta. We're gonna do it symbolically. We're gonna do it symbolically. Don't worry about it. Water goes up to here. There's gonna be a distributed load where at the top, okay. So the interesting thing is at the top it's 0. Right? Wait, I think. Atmospheric pressure? Okay, it's not exactly 0. It's something like this. You know, and then there's big down here. That's our distributed load. We love that. Love to see it. I don't really know why I drew that line. I don't need that line. Uh-oh, I drew it outside the lines. He's gonna come get me. There we go. Saved. Oh, and then we have a cable. So this is FT. This is FP. We have a weight. That's gonna go down. F weight. I guess I should put some dimensions on here. Oh. Yeah. I was like, do I need to draw that line? But I don't. 6. Nope. I'm gonna call it H1. And I'm just gonna call, yeah, this one could just be H2. Let me move these in here. There we go. You got that ANSI standard, if you know what I mean. Kind of a little goofy, but I think that's everything. Oh, there's a hinge, so we have a point force here. I guess I could call him R. Oh, we need a coordinate system. Now he's always going on about, what is it? It's gonna say reasonable. Unapplicable? No. You get the gist. A good coordinate system. What do we think? Bottom of the gate? I'm kind of down for bottom of the gate. But that means that like when we integrate, we're gonna be integrating like up. We're not really gonna be integrating that load. I'm just gonna draw it as a triangle. I'm gonna draw it as a triangle because that's what I do for CE, and well, a triangle and a rectangle, and that's all you gotta do. I mean, I could probably do it as a trapezoid faster, but who cares? I guess we could do a tilted chord. Nah. We're trying to find that force there, and everything else other than FP is gonna be... I'm gonna choose Cartesian. I'm gonna go this way. I know you're thinking, Damie, you mad lad. It's fine. Don't worry about it. FBD. 3 big dogs. Woof. Friction in the hit is negligible. Okay. We're gonna turn into a statics problem. So I'm gonna just say FP. Okay, so that initial is something like this. Wait, hear me out. This is FP. This is height 1. This is height 2. So FP equals, this is, I guess this is like FP1, and this is like, I guess I should say FP initial, FP final equals FP initial times H1 plus FP, final minus FP initial 1/2 times H1. Sure. I can pull out the H1, but I don't need to do that right now. So FP initial equals 1 ATM. What does he want it in? He wants, okay, let me think about this. We're gonna want pounds force, not ATMs, but it is 1 ATM. So let's convert that. What did we say it was? 14.696? Something like that. Oh wait, I can just look it up here. Awesome, I love having reference. It's on like the second piece of paper. 14.696, let's go. Equals 14.696 pounds force inch squared. We are in feet, which sucks, I guess. Do I have it in feet? Man. No. Of course not. And then FPF is what? Let's see. Equals rho GH, or you know what? Gamma H, because I'm so cool like that. It's water. So what is gamma for water? Something. That's gases. Water. What temperature are we at? What's average? What's like normal? 25, I guess. What's 25? C to 77. Ugh, kind of hot, isn't it? What's our kind of standard for water? Oh, it's gonna, never mind. I didn't even look at the table. It's 1.94 slugs. Wait, it's not giving me the... It's not giving me my cool number. It's not giving me my gamma. It's giving me a density. What am I, a pleb? Okay, fine. Gravity's in feet per second squared. That's gonna be pound force. Okay, fine. Rho GH. Of course. Equals 1.94 times 32. Or slug. Feet cubed. I could just move this down here and have a much better time of it. There we go. I'm gonna assume he's gonna let me write these things on one line. He's like, only put one equation on each line. But like, bro, this one I'll leave out. This one's bigger. 1.94? Yeah. Maybe it's 1.93. Let's try that. Slug times 32.2 feet per second squared cross 2 cross times H which is feet. We're gonna end up in pounds force per foot squared. Yeah. What is H? I guess H1. So 1.93 times 32.2, 62 point. Oh, I had that in my calculations already. Pounds force I guess I should say times h1. Per foot squared. Okay. Oh, we're in feet squared. This one's not in feet squared. So we'll do that. Well, that sucks. That's gonna be a big number. Well, actually, I guess it doesn't really suck that much. Well... Wait, Wait, I'm dumb. The difference is... Oh, the difference, is not... Okay, it's, Okay, no, it's not that. Wait, is that... Sorry. I'm just gonna call it delta FP. Because there's still atmospheric pressure down there. So I don't necessarily have to worry about it. I don't have to calculate it twice, is what I'm saying. Times 12 squared is gonna be so big. Am I doing that right? I feel like I'm not doing that right. 1 ATM in pound force foot squared. Oh, okay, it is that. I mean, I guess that makes sense. If we're saying it's 14 per inch, it's gonna be more per foot. Not gonna be less per foot. That'd be weird. Okay, coolio. We're winning. What do I do? I forgot. Okay, we find FP. And it's gonna be at, we'll dimension it later, I guess. So... That's like so many sig figs that I don't need, but that's fine. 1/2. Okay, wait, let me think about this. It's fine. I'll do it out. I don't want to just give too many steps. Times 62.1. Uh-oh. Is squared? Okay. Okay. Interesting. That means I can't really do what I want to do. I wanted to get a number, but I can't. Awesome. Awesome. It's fine. 31.073. I guess I can do that. That's not too bad. I'm so sorry. It's not my mic. I just whacked you guys. Oh wait, it's not gonna be... Wait, I need a force. Let me think about this. Oh shoot. Per area. Ooh, it's the pressure times the area. But I could just multiply the whole thing times the area? Right? And do those areas, do those heights cancel out? I'm trying to think. Oh, yeah, because... Yeah. Heights are not going to mess with units, but we do need an area. I guess I could just... The whole thing by area? Is that correct? I'm just going to pop an A in there. Because that would, you know, that's a thing we can calculate fairly easily. To be fair, we don't even really need to calculate this right now. I'm gonna do this. Watch this magic. Okay, that's not the magic. Me There we go. Not drawing straight lines. We can just say... Here, wait, I'll do what my CE professor does. The squiggly line for a distributed load that's been condensed into one load. That's really quite an easy problem. Okay, and this is at h1 divided by 2. And this is ft, and then we gotta take some moments, baby. We had to take a moment about... Sorry, I got distracted. By this. So this is 90. This is theta. This is 90 minus theta. This is 90. This is theta. There. Just for me. That's some clean lines I drew there. They're straight. They're not perfectly... That's pretty good. That's pretty good. Okay. It's almost like I'm supposed to do that or something. Okay, some of the moments about hinge. What's our positive convention? Our positive convention is this way. Should equal 0. Assumption. Fluid is static. So we get, what do we get? Oh man, we get 2 components, are you kidding me? Okay, well we'll do ft, that's positive. Plus, times, sorry. Okay, H2, sine theta? Yeah. And then plus, okay, no, it's okay, it's okay. It's gonna be minus fp h1 half h1 over 2 sine. Is it positive and negative both ways? Pushing down, and yeah, it's negative both ways. Okay. I can just do this. Watch this. Magic. Bam. Less writing. Yeah, because it's this way. That one will be cosine. This one will be sine. They're both from H2. Nice. And then we just have to solve for ft. Fp. H1 over 2, sine theta plus cosine theta, divided by H2 sine theta. I don't even want to plug in the numbers, man. And then just plug in this, you know, there you go. Okay, I'm just gonna do it for the meme. 2116.224 plus 31. Oh, nothing even cancels out. That's great. I love it. I'm being very sarcastic. I mean, I can do this. Over 2 H2 sine theta. Oh, you know. Just my casual guy. And then we just do some of the forces and whatever, and then, yeah. It's not done, but it's like, it's close to done. The only hard part is none of it. It's literally just a statics problem. And not even a hard statics problem, so sorry. Well, it's not very daunting, I guess. Unlike any of the other ones on here. This one is more interesting. This one is definitely more interesting. This duder here. Also, one of the fascinating things, I have no idea what he's gonna put on this exam that's coming up. We have an exam this Friday, the 19th, and like, we haven't, like, he hasn't, like, he's given like these homeworks, which are like really hard for most people. I say for most people because you guys see that, like, I mean, they're hard, like, I'm goofing it, but, you know, that's classic goofing it. You know, you goof it all the time, even when you know stuff, but like, people are like, I don't even know how to do any of these problems. Like, this one is exciting though. A is a statics problem. B is a fascinating problem. Is this wall safe from overturning? If it overturns, about which point would it rotate? That's kind of crazy. I think, let me see. Oops, I crunched my fluids somehow, but oh my god, I crushed it so much. Oh yeah, no, I was right. It's absolute, it's the atmospheric pressure up at the top. Never mind, I didn't even need to check that. He literally, like, has taught us nothing, which is so funny because it's like... because it's actually fascinating because you don't really need to know that much to do these. But also you need to know... you need to, like, be able to think about things. And I feel like people don't know how to do that. Okay. I guess we just start with A and see where the world takes us. Okay, to keep the wall from sliding. So it's not affixed to the ground, so it's a dynamics problem, and we're trying to say when is acceleration 0. So A equals 0 for what B? That's what we want. So we gotta set up a little dynamics. Oh, he also wanted us to do this. There we go, that's my free body. My free body. I really don't think that's super necessary at this point, but I can see where it could be necessary, so I'll humor him. So we have a weight, and that weight is going to depend on B. I'm gonna draw it real big. Okay, so we got a weight, and then we got this type B. Oh, it's okay, it's not fully submerged. This is P0. Just makes my life slightly harder. Get an extra 2 inches out there. P. PO plus, I'm gonna say PO plus delta P. Plus rho GH. Plus, there we go. There we go. Oh, you can't even see that. Plus, oh, there we go. I wrote a gamma instead of. That's how the big brain boys do it. Write one less letter. I'm just gonna call this H1, 2, and this H1. Yeah, is that all we need? I think that's all we need. Okay, I'll draw some extra arrows in there. You get 1 extra arrow if it's a distributed load. Okay. Do we have a... Okay. Do they give us a freaking, like, weight of concrete? What is this thing? It could be, like, made of cereal for all I know, and that would very much change the problem. Nope, they just don't. Okay, cool, thanks. I guess this is concrete, so I guess we can assume that it's concrete. I feel like that's, like, very not specific. Aren't there, like, a bajillion types of concrete? It's concrete, baby. Okay. I'm dropping. What do we start with? I don't really want to start with the water, but we should start with the water. It's not hard, it's just annoying. 1.94? No, I have to add the 2. I should just memorize 2116.224. What if I just pull that out? Hey guys, 211.224. Oh, you know. Fully based, Damie's still alive? Yeah, I'm still here. Oh, you know me. Just pulling out the 2116.224. What is it? 193? 194? 193, I guess. Slug. I'm just gonna say this. Watch this. H1. Pounds force per foot squared. Nope, I lied. It's 63 point... I did this work already, so I'm not gonna... 62.164. 146. Dyslexia. Okay, H1. Cool. Okay. The force is gonna be the exact same force. I don't need to even redo this, man. I did this already. It's 2116.22. How deep is the concrete wall, huh? How deep is it? Oh. Oh, they don't give me a deep. They don't give me a depth. Am I supposed to assume that it's just nothing? I need an area. It can't just be... Hello? What did I copy? I copied the wrong thing. I want this. Oh, I see. I want that. There we go. I don't need to rewrite that. I did all that work already. There we go. I can do the conversion, but I don't really care. Okay. An A1, I mean, I don't know how deep it is. Unless we just say A1 is also H1. Which is not an area. It needs to be an area. If it's infinity, then it's no force, so I'm surprised they don't give an area. I actually don't even know what to say about that. Assumptions. Wall depth is... I don't even know. Wait, would it matter? Because then you'd have more water. The deeper you went. But I need a pressure. I can't just say pressure. But it shouldn't matter. Because, yeah, the deeper you go, I mean, like, the water is also going to be that deep. So maybe it is just times the height. But, like, we multiply by the height already. For the distributed load. Which I guess is kind of like... Because this is in pounds per foot squared, and this is in pounds per... That's just in pounds. But that H1 is because the H1 is no, it's in pounds per foot. Which I guess means that we multiply by H? I don't know, man. Pounds per foot. Pounds force if I multiply by H? I don't know, that one's weird. I'm gonna put a star. Units / area? There's lots of question marks. Okay, fine, it's fine. Whatever, it doesn't really matter what the force is. Again, we kind of said the same thing about that last time. I have to draw the MAD. A equal... I don't know if I need to draw an MAD. There's no forces. Oh, wait. Friction. Yes. There's no forces. Me, when I literally always forget friction. I'm such a friction hater. I'm so sorry, guys. It should be static. Oh, I guess it's just friction. There are a lot of things I need to figure out here. The weight is more for a moment than it is for a the acceleration. So what we need to say is for some of the forces in X equals MAX 0. Here, I'll draw the tiniest MAD. MAX 0. do you like my KD? I don't really know if that's necessary, but sure. Sum of the forces in X equals 0. So we have FP equals FF. Sorry, FP minus... Oh, I didn't put a coordinate system. Actually, a good question. Do I want to put it around the middle? I feel like I low-key want to put it around the middle. Or I guess I could put it at the bottom of the distributed load. It doesn't really matter. Because it's just gonna... It doesn't matter at all. It doesn't matter at all where it is in this case. But fine, I'll put it at the bottom of the distributed load, just so that we can say everything is in our positive x direction. Or included on the right side of our coordinate system. FP equals okay, N. Now tipping point or slipping point, slipping edge point. I just wanted to say edge, I'm not gonna lie. Slipping point FF equals mu sub Fn. Yeah. So okay, sum of the forces in Y equals MAY 0. Sorry, there's a normal force here too. Lol. I'm gonna do a cheeky little drawing it up. No, I'm kidding. I can't draw it up there. Man, I made my force way too damn big. Your damn weight force out of the caption. There we go. The normal force. So normal force minus F weight equals 0. The normal force equals F weight. Now what is the weight equal to? The weight is equal to mg. And then m equals density times volume equals density times but we need a volume. We need a depth of the wall, do we not? Or do we just not care? Should I just say area? Should I just say area? I'm gonna say area. It seems like it's like a 2D problem and we're gonna like discount the third dimension as like it's repeated the same throughout the whole thing. B times H2 plus H1. Yeah. Kind of a weird way of defining it. I probably should have defined it H2. But it makes my life... Nah, it's fine. It doesn't matter that much. Okay, so FP equals what? I don't know. Mu sub F times rho B H2 plus H1 times G. Sure. Sure. And then what was I trying to find? I don't remember what I was trying to find. Some ratio, I think. Oh no, what's the value of B? Yeah. I think I could solve. Because so FP is gonna be in like H1s and H2s, and then I'll have a B, and I have a rho I know, and that, and H2, H1 I know, and F I know. Okay. That's basically solved. Just like stupid about it. This is still the easy parts. Is the wall safe from overturning? This is the interesting one. I want to see. So if we take a moment about here, there's going to be like a distributed load here. Right? And the weight force also pushing it there. So it's going to want to go up. Like it can't really turn this way because the normal force is like here and it's kind of constraining it like a lot. But if we take a one here, this one pushes this way, but the weight pushes this way. But there's nothing stopping it from... These two are going to cancel out. And the only one we have left is that. But does that also happen here? Yeah, but the normal force is here as well. Whereas the normal force is like here onwards here. So it's going to turn about this point. Which I guess makes sense. Imagine if you were like pushing like a box or something. And it started turning... Wait, I got a gamer portrait. There we go. It started turning like... I don't even know how that would happen. How did it happen? No, you literally can only turn about this point. There's no way you could turn about this point. It started rotating into the ground. Whoa. Damn, bro. Your box is rotating in the left corner. Or it started rotating towards you that way. That doesn't make any sense either. Yeah, okay. I like that. I like that. Yeah, rotates from the back corner. Assume that water does not penetrate underneath the block. Perhaps you can present your results for safe and unsafe conditions in the form of a plot. Okay, what would change that? The higher B is, the worse it gets, essentially. because your moment needs to be kind of offset by the weight. That's a fun one. I want to plot that at some point, but not right now because I don't want to do that. But I could plot the whole thing in MATLAB. Okay, if water does penetrate underneath the block, sorry, will this help or hinder overturning of the wall? Everything sucks if it gets under there, guys. Guys, I'm gonna be real. It sucks bad if it gets under there. Like, if this is your wall, you are so cooked. Because it goes like this, so it's gonna keep pushing it this way. And it's gonna be pushing it this way and this way. Sorry, not like that. It's gonna be pushing it this way and this way, so it's gonna be like mega rotate. Because we can say there's a distributed load, sort of like this, and one that's like this, yes, like that, because the biggest one will be here, or it like approaching there, because it's deeper, and so it's gonna be like, this will be here, pushing it this way, and this will be here, pushing it this way, and you are so boned. Life sucks if it gets under there. I've drawn Master Shake. I don't like Master Shake very much. He's kind of an asshole. There we go. He's gone now forever. Okay, maybe I could plot that. Do we want to plot that? What if we just like mess around in MATLAB for like funsies? What if I just put all these values in MATLAB and we just said, okay. I'd kind of be down. I've kind of always wanted to solve problems like this just by saying, fuck it, we ball in MATLAB. I have it right here. Let's do it. Let's do it. This is not the correct problem. This was problem 5. I don't know. That was our... Oh, use of brackets is unnecessary. Thanks, MATLAB. Really saving my ass. Okay. I don't know why I said homework 2. This would be like P5, and this should be P7. Okay. We gotta get some variables in here. We need a height 1 equals something. Height 2 equals something. I don't know what else we had. Okay, we're assuming the pressure is atmospheric pressure, 1 Earth, whatever. We need a rho. I'm gonna call it rho. Density. We need a mu f. That's 0.4. We were given that. The depth of the water to the left of the wall is 12, and the height of the wall is 14. It'd probably be better to maybe not do this then. But it's fine. The water is 2 feet higher. And density is... I don't know. We haven't figured out the density yet. I have to look that up in table. Wait, but concrete's not a fluid. Guys, wait, maybe it's in the thermo handle. Wait. The cheese, the Swiss cheese, maybe. Wait a second. Properties of engineering, materials. Concrete. Cured. Specific gravity. Specific gravity is rho g, right? Oh, they're nice. They gave us... Wait, we can go and change that for alpha in our equation. Oh yeah, baby. This is great. Okay, we're gonna do rho g. 2.4. Depends on aggregate. Thanks. Thanks, bro. Wait, here, let me change this over. Okay, we're gonna change it. I love having one less value here. That's our specific gravity of our concrete. I'm actually becoming a massive specific gravity fan. This might be one of my favorite constants so far. Okay, so not dense, this is gonna be spec grav equals, what do you say, 2.4? Now 2.4 what? This is 2.4... It should be okay with units, I think. And then we're gonna say... I'm gonna have to solve for B real quick in my head, but we can figure that out. Yeah. I'm really excited to see what a plot of this looks like. Okay. But this is gonna, we're changing the depth of the wall, or the depth. The only thing that's weird is my pressure equation. Pressure in 2D is probably just like a line, I guess. I guess. Maybe. Anyway. I guess we just have to say what B is now. Okay, so B equals... I'm gonna do this one first, okay. FP... Oh, I can just write an equation for FP too. Okay, FP divided by mu sub F... mu sub F times spec grav times H1 plus H2. And then FP equals our... What did I say? 2116.224 plus 31.063. Nope. H times H1 times H1. That's so exciting. Oh, I love not having to calculate things. This is like riveting. This is squared. I think. Maybe. Wait, let's see what B is gonna be. What do we get? Okay, that's really high. Is that feet? Oh, you can't even see how high that is. I don't know if that's right, guys. I don't know if that's right. Here, wait, let's... Wait. Here, I'll crop that out. I don't know if... Don't know if that's right, actually. Here we go. You guys down here for now. I don't think that's right. So it says that it's in feet, right? Is there anything that we did wrong in units? Well, the thing that... Yeah, it's in feet. What if we plotted B? So, okay, if we plotted B, that would mean that it's not going to equal 0. It's gonna... Well... No, actually. That's an overturning thing. That's a moment thing. We need another equation for that. This will still always be true, because we don't want the wall to slide. It definitely does not need to be... What is that? 2,000 feet? It does not need to be 2,000 feet. It's more than 2,000 feet. That's... It's 20,000 feet. 26,000 feet. Okay. Okay, edgelord. Maybe it's something with the... No, pounds per foot squared. Okay, let's think about this. We're gonna come back to this one and change this to... Oops, change that to that. There we go. So we know this is right. This is correct. We're chilling there. But we know that this... It doesn't really matter right now. Okay, so we need to turn these into forces before we can sum them up, is what I think is the issue. So pressure equals force over area. Not force times... Wait, no, but force equals pressure times area. Okay. So we need to change this definition. Get out of here. Okay. FPO equals 2116.224 times... So this is pounds force per foot squared. I think there has to be some... There has to be something I'm missing here. Because if I say pounds force... Right, if I just multiply by, like, the height, for example. We say that's our, like, sort of area. It's just, like, the line. Then our units are going to be pounds force per foot. And that's not it. Our thing is determined by the slope of our distributed load is determined by the density of the fluid. Not the intercept here. This is just an intercept to our line. And I don't really know what's up with this area. So I'm trying to think, if we were to have a 3D surface, would that change anything about the pressure? So pressure only varies with in our case, y height, right? So with depth. Pressure only varies with depth, which means that the pressure would be the same if we went in 3D and we went back along the wall. And that means that our force would be the same if we went along the back wall. But like as we accumulate area backwards, we're gonna accumulate more force. But the question is just like, I can't get this in like pressure is equal to pounds force over feet. That's like, doesn't exist. Pressure is a force over an area. It's not pressure force over a length. Because what I get out of this is a force over a length. If I want to say, oh, okay, this pressure is distributed over H1, which it's not even. This pressure is only here. If I sum up the pressures, because it's a pressure gradient, I can get a sum of all of the pressure that translates to one pressure here. But that doesn't give me... It still doesn't give me an area. Well, I guess it does give me an area. Am I just not reading something right? Is this B like... Is there like, oh, also the waters are... Wait a second. Wait, I'm cooking. Give me a second. Wait a second. Multiply by feet. That's this part. It's that part. Okay, I need to change that. I'll need to change that. Or no, I plugged that in, I think, last time. Yeah, it's the 31 point. 31.073. Now this is also over a height. And then I think we multiply this by h1. Because if we say, like, okay, our pressure is over here, and we're trying to figure out, like, how much pressure we have. It's over this amount of, like, this little line, and then we say, okay, this one is over, like, you know, this little line or whatever. They're both stuff that's over this little line. That's going to change the units. And then if we say force, it's going to be this. And why did I have a squared in here before? Am I okay? What was happening there? Oh, because I was just multiplying. Oh, because there's a rho GH. Yeah. No, there is. Wait, no, that's rho G and then times H. Why did I square that? What? What was I doing? Okay, I don't know. Maybe I put an extra H in there. I don't know. Anyway, I think it's just this times H squared. H1 squared. It's my best guess. So it's a little different than what we had. It's not 31 times H1. It's just those two numbers added. And then okay, B still equals 3.2 times 10 to the 4th. 2.3. Fuck, what is that then? It has to be some, like... Is it a conversion thing? Okay, wait. So we have... Okay, let's assume this is right. mg, m equals density times area. That's another weird one. It's because, like, I guess we just need to kind of, like, take a slice and think about it, but, like, for pressure, it's kind of weird as hell if you think about it. Oh my god, I've been streaming for 2.5 hours? Okay, I need to... I need to leave. I did not think... I was like, oh, I'll just work a little bit more on this problem. Maybe it's the specific weight of concrete? Specific gravity? No. I don't know. I'm trying to think about where this could start getting, like, exponential. Expect exponentially bigger. That h1 squared in feet is probably what's partially doing it to us. But we're dividing by Oh no, it's probably this big chump over here. That atmospheric pressure. What if we just said it was in a vacuum, you know? What if we said it was in a vacuum for fun? No, I think that's supposed to be PO. I feel like I'm just off by like an order of magnitude or so. I feel like it's like 2.3. Like I'm off by 4 orders of magnitude somewhere. I think one of them is coming from here. I think some of it is coming from here. Yeah, well, we'll have to figure it out next time. It's a mystery that shall be left unsolved for now. It's a little bit longer stream today, everybody. Thanks for hanging out. I think I'm gonna try and... stream... Maybe I'll stream... No, I'll stream Tuesday. Yeah. That works. And then, you know, we'll have made some headway on this, and that should be great. Alright. I'll see you guys later. Thanks for hanging out. Bye.